Okay, we're going to learn something called an infinite limit. Infinite limit, we know the symbol this means infinity. And this is a positive infinity, and this is negative infinity. We're going to use those symbols a lot. Okay, so I give you one example. Here is a function, f of x equals 1 over x. When you graph it, it looks like this. Okay, this is 1, 1, this is negative 1, negative 1, and this is f of x equals 1 over x. All right, now let me ask you a question. What is the limit x approaches to 0 from a negative side of this f of x? So x approaches to 0 from the left side, the y value goes down and down. So that is negative infinity. And the other side, the limit x approaches to 0 from positive side to 0, that 1 over x it goes up. So it's a positive infinity. All right, so this is just a simple version, or it's just a simple way to look at that. But if you remember that when we have the definition, we have a formal definition of limit, and we have the epsilon delta. I hope you still remember that, okay? So the epsilon delta, okay, what it say is, I give you for any given little number epsilon, okay, we can find a delta, okay, and that x is the distance between x and the c is between 0 and the delta, and that makes the f of x, or f of c, minus L is less than the epsilon. So we can find this delta such that for the x value, it's within plus minus delta of c. That f value, f function value at x minus a certain number is less than the little given epsilon. So that is called the limit. Remember, that's the formal definition of it. But this x right now is a fixed number. However, when we talk about the infinity, positive or negative infinity, the definition will look like this. Okay, for we don't have epsilon because epsilon is small, and then we're going to do something else. We're going to do n. So let me give you a quick example. If you go like this, it goes up. Okay, so here's a c, and then I can put any as big as possible, whatever big M. So given big M, that's greater than 0, and actually it's a huge number. And we can find epsilon such that x minus c absolute value is less than epsilon and greater than 0, such that f of x is greater than m. So which means no matter how big that m is, we can always find, no matter how big this m is, we can always find a very small distance from c to like this side. Let's say this is the left side, and then there's a certain little distance that for any number in between this c minus delta and c, such that f of x is greater than this given number, like this one. Okay, that's the definition is. If we can find the x is less than delta, less than c, and c minus delta, if that's the case, so that's the left, right? So we call this as limit x approach to c from the left side, f of x equals infinity, positive infinity. And this shows f of x, the limit when x approaches to c equals infinity. It doesn't matter whether it's positive or negative. This is the negative side. Of course, the right side is going to be from c less than x less than c plus delta, which is the right side, and that is gives you x approach to c plus f of x equals past infinity. So far this is for past infinity. If you give a huge m, and in another word, if I give you a very negative number for given n, which is less than 0, we can find a delta, and this x minus c is less than delta less than 0, such that f of x is less than n. Okay, so no matter how low or how negative this number is, we can always find a delta such that when x is really close to c, that f of x is less than that. So no matter how low that no matter how low this number is, this n, we can always find an epsilon such that for any given this little interval, any point or the point in this interval, their y value is less than n. That tells you that limit approach to c f of x is negative infinity. So positive or negative limit definition is a little bit different, but it really doesn't matter. You get the idea, that's it. Okay, so I would give you a couple of examples. I want to show this. I give you h of x, which is f of x over g of x. So there's a function. This function is a quotient of these two functions. For x equals c, the numerator f of c is not 0, but the denominator g of c equals 0. Then the limit x approach to c, h of x will be infinity. Okay, makes sense? Because the denominator is almost 0 and the numerator is not 0. Therefore, this h is going to be infinity. But sometimes it's positive, sometimes it's negative. Let's see what happened. I'll give you several examples. The first example, h of x equals 3 over x plus 5. I ask you to find the limit x approaches to negative 5. H of x. See, this h of x is 3 over x plus 5. It's like f over g. And this f is not 0, no matter what x value is. This g, when x equals negative 5, this denominator is 0. Therefore, this is infinity. Okay, that has a infinite limit. But we know that for limit x approach to 5 from positive side, when x approaches to that from positive side, when x is, did I say negative? Yeah, negative 5 from the positive side. Sorry, x approach to negative 5 from the positive side, which is the right side. So, which means a little bit greater than negative 5. Then you plus 5, you get something a little bit above 0. Okay, so if this one is a little bit above 0, it's still positive, so that will be past infinity. But the limit x approach to negative 5 from the left side. Okay, when x approaches the negative 5 from the left side, the denominator is a slight negative number, very small negative number, and then 3 over that, so you get a negative infinity. So that goes back to something looks like this, right? This example. So the one side go past infinity, the other side go to negative infinity. And that means this limit at this moment, it doesn't exist. Even you have something look like this. Okay, Even the left limit and the right limit are both a positive infinity. That limit is still, we call that does not exist. So don't be confused. When we say the limit exists, only when the limit is a fixed number. Make sense? Okay, so one more. We got a lot of examples right now. So what about h of x equals cosine x over sine x? We know this is a cotangent, right? Okay, so I ask you to find the limit when x approaches to pi. Cosine x over sine x. If you plug in x equals pi, sine pi is almost 0. It doesn't matter positive or negative, it's almost 0. But the numerator cosine pi is -1. So the numerator is not 0, but the denominator is 0. So that is infinity. Whether it's a positive or negative, it depends on whether you approach to pi from which side. Okay. And one more. H of x equals x plus 1 over x squared minus 1. Well, we know the numerator is x plus 1, the denominator is x plus 1 times x minus 1. Okay, now can we find at which point that we're going to have an infinite limit? And it's the numerator not 0, the denominator 0. That c will make us to have a infinite limit. So in this case, if you cross this out, when x approaches to 1, the denominator is 0, but the numerator is not. So x equals 1. That will give you a infinite limit. That's not a problem. But what about when x approaches to -1? Okay, so when x approaches to -1, we get a numerator, we get close to 0 or approach to 0. The denominator is also approach to 0. So will that give you a infinite limit? Not really. You're going to have something looks like this again. Okay, sorry, this is it's 1, so it's going to be look like this. Here's a 1, so you're going to have something looks like this. All right, so when x approaches to 1, see, you get an infinite limit. But when x approaches to -1, you get a circle here, because that point is undefined. So if a number x value c, if you plug into the numerator and denominator, you get a 0 over 0. It doesn't necessarily mean that at this point you're going to have infinite limit. It doesn't really mean that. It doesn't have that direct relationship. You have to do a little bit further investigation. Okay? And let's see. Can we find what is the, can we find this one? For this one, h of x cosine over sine. Okay, h of x is cosine x over sine x. Can you tell me, this is a cotangent x, right? Okay, can you tell me at what x value you are going to have an infinite limit, which is what x will make this to be 0, but this is not 0, isn't it? So what makes the sine x to be 0? Sine x to be 0, that is is n pi. N is an integer. Okay, it's like a 0, +1, +2, +3, and -1, -2, -3, etc. So when x equals n pi, then the denominator approaches to equals 0, and this is not a 0. So this is where you're going to have the infinite limit. Is that right? The cotangent curve? The cotangent curve looks like this. I don't know if you remember that. See, when it's a 0, and here's a pi, and here's a 2 pi. See, when x equals 0 pi, 2 pi, or negative pi, negative 2 pi, n pi, that will give you a infinite limit. That's perfect, right? It agrees what we learned. Okay, so one more question. To find a limit. Oops, sorry. Okay. Sorry. Okay. Find a limit. What's wrong? Find limit. Limit x approach to 5 from negative side, and the numerator is x squared plus 5. The denominator is x minus 5. When x approaches to 5, the numerator will be very close to, that's just 5 squared, no matter whether it's approaching from positive or negative side. So that x squared, that's 25 plus 5, the numerator will be really close to 30, isn't it? And the denominator, if x approaches to 5 from negative side, minus 5, that will approach to 0 from negative side. So that's going to be a very tiny negative number. So that answer is negative infinity. So it's fairly simple. You can just by looking at that. Okay. Now, if I ask you to give me this, what's the limit x approach to 5 from positive side, and x squared plus 5, x minus 5. The numerator x approach to 5 from positive side, you square it, you get 25 plus 5, so that goes close to 30. Yeah, you can put that. It doesn't really matter. And when x approach to 5 from the positive side, x minus 5 will approach to 0 from the positive side. So this answer is positive infinity. So a lot of questions like this, it should be very easy to read it and to get the answer. All right. Now, in this case, when x approach to 5, because you approach to 5 from both sides, then you get a different answer. One is positive, the other one is negative. Then we're gonna say, well, this limit does not exist. Okay. So limit x approach to 5, x squared plus 5 over x minus 5, you just tell me does not exist. Is that simple? Okay, now for this question, for those functions with infinite limit, and there's a lot of properties. Gosh, we get so many things, right, to learn. Okay, so if we have like a limit when x approach to c, f of x is infinity, but the limit when x approach to c another function is a fixed number, then limit when x approach to c, f of x plus g of x, which is about a infinity plus a fixed number, is also infinity. Easy. And then the limit x approach to c, f of x minus g of x. So an infinity minus a fixed number is also infinity. Okay, I could keep going. So limit x approach to c, f of x times g of x. Now, this is a infinity times a fixed number. So that will become either positive infinity when L is positive. Okay, so the limit of g is positive, then this product becomes or equals positive infinity. It's negative infinity when L is less than 0. Okay, but when L equals 0, when L equals 0 means the limit of g is approaching to 0. You want to multiply by an infinity? We don't know. We need more work. Okay, don't do anything. Okay, you need more work. And then, so add, subtract, product, quotient. Okay, so the quotient is this. Remember this f limit, I have to write it, approach to c, f of x is infinity. Limit x approach to c, g of x is just L. Then what is the limit x approach to c, g of x over f of x? So this is a fixed number, and this approach to a fixed number, this approach to infinity, and that limit is 0. Make sense? Because any fixed number divided by a huge number, then you should get 0. Okay, again, we're going to have a more example. The first one, limit x approach to 0, 2 plus 1 over x to the 4th. When x approach to 0, this is 2, and this is like a 1 over like a 0, and to the 4th, that's even power, so it's always positive, so this is positive infinity plus 2, so that's positive infinity. Okay, so that's my first example. So I'm using the property of, first of all, I use addition, okay, and then I just go ahead and do it. Next one, limit x approach to 3 from a negative side, x plus 2 over x squared minus x minus 6. Now when x approach to 3, see this is a 3 squared 9, now 9 minus a 3, 6 minus 6, ooh, the denominator becomes almost 0. But the numerator is not. Numerator approach to 3 plus 2, that approach to 5. So that is a number divided by a 0, so that's infinity. Isn't it easy? But when it's a negative 3, when it's when it's a 3 from the negative side, so this one, x plus 2 on top, and the denominator, you factor that, you get x plus 2 and x minus 3. So this is approaching to 5. This one also approaching to 5. You're going to cancel that out, and you get a 1 on top. Denominator, x approach to 3 from the negative side. So x minus 3 will approach to 0 from the negative side. So it's a tiny negative number. Therefore, this should be negative infinity. That is your right answer. Okay? All right. Factor, right? So next one. Limit x approach to 3 from the positive side, and x plus 2, here x squared minus 9. Now x approach to 3 from the positive side, the numerator x plus 2, that will be close to that approach to 5 from positive side. But look at the denominator. X squared, x is approaching to 3 from the right side. So x squared is approaching to 9 from the right side, right? Slightly over 3. So x squared will be slightly over 9. Minus 9 become like a number slightly more than 0. So that will approach, denominator approach to 0 from the right side. So that answer is positive infinity. That's fairly simple, isn't it? All right, now next one. Limit x approach to pi over 2 from the positive side, and I have a 2x over tangent x. Okay, when x approach to 2 pi from the right side, double it, 2 times x, that will approach to pi from the right side. That's the numerator. And the denominator, tangent x. Tangent x, when x approach to pi over 2. The tangent x graph look like this. Okay, here's pi over 2, and here's a pi. Okay, that's 0. This is the tangent curve. So when x approach to pi over 2 from the right side, and the tangent is almost like it's approach to, it's about 0. Okay, it should be like a positive. Oh, sorry. Approach to pi over 2 from the right side, you get a negative infinity. So the denominator is almost like a negative infinity. And the numerator is not a 0, so the answer is just a 0. So I think I just get a little confused somewhere. Okay, now, after we deal with all those infinite numbers, I really want to talk about the asymptotes. We look at this. There's where was the one that the point is? Okay, this one. Okay. Did you notice that I asked you what happened when x is approaching to -1? And when x equals 1, see, we have when x equals 1 in this case, the numerator is not 0, but the denominator is. If that's the case, then we have a vertical asymptotes. Numerator not 0, denominator 0, that will give you the asymptotes. So this give you the asymptotes. So this one, okay, cosine over sine, the h of x. When x equals pi x, the denominator will be 0, but the numerator will not be 0. The numerator could be, cosine n pi will be either +1 or -1. So the numerator not 0, but the denominator is 0. So that x, this number will give you, n pi will give you the vertical asymptote. So how do you determine a vertical asymptote? That is the c, make the numerator to be non-zero, but make the denominator 0, and the x equals c will be your asymptotes. So I will ask you this. Can you determine the asymptotes for this function? Okay, for this function, what x value will make the denominator to be 0, but the numerator is not 0? The denominator 0 is 0 pi, right? That will make the denominator 0. But, sorry, this denominator 0, that's here and here, right? But then the numerator not 0, yeah, it's not 0, but when x equals 0, then that's not 0. So tangent pi over 2, okay, so that is, that's sine x over cosine x, right? So what x will make your denominator, what x will make your tangent to be 0? That's when your sine is 0. So that's 0 and a pi and so on. So where the vertical asymptotes, it's going to be, I couldn't graph it because this is the tangent. I couldn't graph it. So it's going to be what? It's going to be whatever x value make the denominator to be 0, which is n pi. But the numerator cannot be 0, so except 0. So n is not 0. So that's the case. So basically it tells you that how do you determine the vertical asymptotes? I got so many graphs. It shows you I got many graphs to show you the vertical asymptotes, and that is when you have the see, this is the vertical asymptotes, right? See, 0, pi, 2 pi, and that's the cotangent. So that is shows you where you get the asymptote. So if I ask you, if in the question somewhere, because I couldn't remember where did I put it. If I ask you, can you determine find the limit, or tell me where the function has or the graph of the function has the vertical asymptotes, just need to find the x value that makes the denominator to be 0 and the numerator not 0. So whatever C make this happen, and that x equals C is your vertical asymptotes. So if you can remember that, I think you should be okay to work on the homework and all the questions. Okay, so for the infinite limit, it's really not too hard, and also it deals with the vertical asymptotes. I didn't really talk about the horizontal asymptotes. That's when something happened that looks like this. So when x keeps going and this y stays like gets very close to that, this is called this function has a horizontal asymptotes. Okay, so I don't need to talk about that, but when you see the graph, you should be able to see it. You should be able to recognize it. I think that's about it for the infinite limit and the vertical asymptotes.